Okay. All right, so over the next 3 lectures, we're going to try to really look at the structure of different enzymes and try to understand the mechanisms of catalysis. So we're going to start out today looking at some general mechanisms that are used by a lot of different enzymes. And then we're going to move on in looking more specifically at a number of different enzymes and looking at their active site and looking at the structure of it and appreciating how that architecture and the side chains that are in the active site, how that's perfectly designed to catalyze whatever reaction we're looking at. And then we'll also look at some of the experimental tools that we use. So today, we're going to talk about general acid-base catalysis, which is common. It's a common mechanism employed by a lot of enzymes. pH rate profiles, the pH dependence. That shouldn't be surprising, right? If we have side chains that are in the active site and they can ionize and exhibit acid-base behavior, and that acid-base behavior is going to give charge or not have charge, and the charge is important for activity, then by extrapolation, we're going to have a pH dependence on that. So we'll start to make inroads into that so you can see what that's about. Then at the end, introduce chymotrypsin. We'll talk more about it on Tuesday after your exam, which is Monday. And at the end, I'll tell you a little bit more about it, try to ease your mind, or maybe not. Okay. So let's look at this hydrolysis reaction. Right? This hydrolysis reaction, what we're looking at here is hydrolysis of an ester, but it is applicable to an amide, and a peptide bond being an amide bond, this plays a role in the hydrolysis of what have we talked about that have these amide bonds? Protein chains. So if you're breaking, and we're going to look at several proteases, we're looking at a reaction where we're hydrolyzing this bond. If it's an X, in this case, if it's oxygen, that's an ester. If it's nitrogen, it's an amide or a peptide. So we're simply hydrolyzing that bond to give these two products. The mechanism goes through a tetrahedral intermediate. All right, and that will become much more clear when we look at the active site of chymotrypsin on Tuesday. All right, but there's an intermediate, which is tetrahedral. Tetrahedral meaning you have that central carbon, and these 4 bonds, 4 groups are spread to the 4 corners of a tetrahedron, and then it's resolved from that intermediate. Okay, so when we look at this hydrolysis reaction, what's going on? Some basic organic. The oxygen is a nucleophile, right? This nucleophilic attack on this carbon has a slight positive charge on it because it's bonded to the oxygen. So this nucleophilic attack is a result of this being electron rich, this being electron deficient. So if we want to speed up that reaction, we could try, in looking at this charge separation, it's not a full charge, but it's an asymmetry in the electrons. If we put something positive here, that's going to stabilize it, right? If we did something to make this more nucleophilic, that would also speed up the reaction, right? We're going negative to positive, positive to negative. So one way that we could do that would be to protonate that carbonyl group, right? If we put a proton on here, that's going to stabilize that structure. Another way would be that we deprotonate the water. So the water here is H2O, but if it was just, let's say, a hydroxide ion, where the oxygen was a full negative, that would also stimulate the reaction. So let's just look at that a bit. What I just told you are two examples of specific catalysis, i.e., when we were talking about protonating that carbonyl oxygen or deprotonating the water. In those cases, we've got acid-base catalysis going on, but it's involving a specific acid, i.e. proton-specific base, the hydroxide ion. So what do we mean by that? Specific acid catalysis, bless you, involves a free proton. So in this case, this free proton that's added here is stabilizing that negative charge and making that carbon more susceptible to nucleophilic attack. So that transition state is being stabilized by a free proton, which would be pH. We'll get back to that. The opposite of that would be, where are we here? Okay, in the hydroxide, what's attacking is not water, but actually the base form, the hydroxide ion itself. So this hydrolysis reaction could be stimulated in this way, but here the base is a hydroxide ion itself. What we're more interested in, all right, are general acids and general bases. So and I'll show that again in a minute. Here, to protonate that oxygen, rather than that coming about by a free proton in solution, it's coming about by what? Something, a weak acid, which can donate that proton, and then you get the conjugate anion, right? That causes that to be stabilized and more susceptible to nucleophilic attack. So the key here is that a general acid, and for our purposes, what might that be? That's going to be a side chain that has a proton to donate. That a general acid is a weak acid which is going to temporarily donate its proton to speed up the reaction somehow. Now, what do we know about catalysts? They don't change. So it undergoes a temporary change, but then it has to be restored. So I'll tell you now, and then I'll tell you again, that if you have a catalyst, chemical or protein, i.e. enzyme, if in an early step it donates a proton, somewhere before the end of the reaction, what must happen? It must get it back. So in this case, if you have a general acid catalysis mechanism, something is going to donate a proton, but then it has to get it back. So if it donates, it's functioning as a what? If it donates a proton, it's acting as a acid. But if it has to get it back later, it acts as a base. So in general acid-base catalysis, you've got this temporary donation of a proton and it'll get it back. So we'll look at reactions and say, well, this is general acid catalyzed or general base catalyzed. But the important point is to realize that during those catalytic steps, you've got both, or those mechanisms, you've got both things happening. That'll become more clear in a minute, right? Similarly, general base catalysis. Water is sitting here and it says, I'd like to attack that carbon, but if I was more negatively charged, right, I could be more nucleophilic. So along comes a temporary hydrogen or proton acceptor, i.e. a weak base. It'll take that proton, making the water now more nucleophilic. Here's the attack, here's the intermediate, and then, again, for the catalyst to be returned later, it has to give that proton back up, and so back here, it's acting as a general acid. All right? On the bottom, can you guys see that? So, the more negative this is, right? And this will become apparent in a specific enzyme that we talk about later. For that oxygen to become more negative, right, it can be stabilized by a positive charge, right? The more negative that is, the more you're pulling electrons this way, the more susceptible that carbon is to nucleophilic attack. So if you have a developing negative charge here, one way that you could stabilize that, and when we talk about stabilizing, we're talking about doing what to energy? Lowering it, right, is to have an interaction here between the developing negative charge and something positively charged, right? So metal ion catalysis or electrostatic catalysis is where you'll have a metal ion in the active site, right? And in this case, that charge on the metal ion is going to interact electrostatically with something, bless you, in the active site and in the transition state to help stabilize it. All right, so we talk about metal ions being present in the active sites. We have a couple of times, we'll see it again. It's because that charge is somehow interacting with something electrostatically to give you a favorable enthalpy, and with respect to that energy barrier, it's going to lower it. All right, so to back up, we could try to achieve some of these reactions or some of this catalysis with acid or base per se, but in water, right, what do we know about the concentrations of protons in hydroxide? They're very, very low. So that's why the enzymes have developed, evolved, been made, however you want to look at it, that they use the general acid base. So I hope that you can see where we're coming, or where we have come from, in terms of why. Does everyone appreciate why, when I said on Tuesday that understanding acid-base behavior was so important to everything? Because, I mean, these proteins aren't terribly complex. You really have these kind of backbones, and then you have, you know, charges that are projecting in three-dimensional space. They get more complicated when we add things called prosthetic groups, which we'll get into, the coenzymes. But really, they're these scaffolds for charges. And whether the charges are there or not are absolutely critical, not only whether they can do something or not, but how they do it. So that's why, and you'll be tested on Monday, you really need to appreciate acid-base behavior and how that applies to the side chains of the amino acids for protein function. Okay, so let's look at the hydrolysis of an ester, and here we're not looking at an enzyme, we're looking at it being done by a buffer. All right, so the buffer is imidazole, and here's one mechanism. In the first step of this particular mechanism, the imidazole here is in the protonated form, okay, and it donates a proton to get to this step. So during this step, that imidazole is acting as a general acid, okay? In the next step, we've got a molecule here of imidazole, which is in the unprotonated form, which it temporarily accepts this proton here from the water. So it's acting as a general base in this. So there are two quick steps before it gets to this tetrahedral intermediate. Now you've got a molecule that's in the protonated form, okay, that functions as a general base, and this goes fast. Everywhere where I've put a green arrow means that that step is fast. This last step here, it donates a proton and functions as a general acid. So if I said in this mechanism, what does imidazole do? Does it work as a general acid catalyst or a general base? There'd really be two answers to that. The first answer is, well, there are multiple steps in the reaction, and depending upon what step in the reaction you're talking about, it may be functioning either as a general acid or as a general base. But then the question is, all right, if we're going to look at these steps and we looked at them kinetically and said, what is the slow step? What's the rate determining or the rate limiting step? It turns out that in this mechanism, this step is slow. So if that's the slowest step in the process, then when we look at the pH dependence for that, the pH dependence is going to reflect the ionization state that is needed for the slowest step, right? If this is the slowest step, then what form must the catalyst be in? The protonated form. So for this reaction, would it go faster at lower pH or higher pH? Lower pH, right? So for it, now this is a little tricky, it's not meant to be, but you just have to think about it. If something is functioning as a general acid catalyst, all right, it has to be in the protonated form. And the protonated form is the what form? When you think about, and we've thrown the term around acid, a lot of times you'll say, oh, aspartic acid, it's negative charge. Glutamic acid, negative charge. Your first impulse is to say, I know acids dissociate, so they're more negative. But when we talk about it in this case, we have to say it with respect to what it looks like prior to donating. Right? So normally you would say acids are negatively charged. Here it's functioning as a general acid. It's donating the proton, which means it has to have the proton there for. Do you see the? Okay. So here's another way you could skin the same cat. In this one, this step, the slow step involves the unprotonated form. It takes the proton from water to make it more nucleophilic. In that case, it's functioning as a general base. It's slow, tetrahedral intermediate. Later, right, it functions as a general acid. So you're always going to have general acid, general base kind of being paired up for a catalyst because it's got to get back. The question is, during that process, from beginning to end, what was the slowest step in the mechanism? And then when you identify that step, you say, all right, what did the catalyst function during the slow step? Did it function as a general acid or general base? If it was a general acid, then that reaction is going to be more dependent on a low pH and vice versa. All right. So again, if you look, the rate limiting step here is dependent on whatever this rate constant is times the concentration of substrate 1, which is your ester, times the concentration of your buffer, in this case, and that is of the unprotonated form. Right? Okay. So this is imidazole. It is a buffer. What does that structure remind you of? Histidine. Histidine has an imidazole side chain. So you should keep that in mind because that's why histidine is present in so many active sites. All right, is that it has a pKa in the physiological range, number one. So we know that it has the potential to either have positive charge or not. And I told you once, and I'll tell you again and show you, what do we know about the pKa's of the side chain of free amino acids versus amino acids in a protein or within the active site? The pKa's, when you have amino acids free in solution, they're invariant. They are what they are. when you put them in the context of a protein and they're surrounded by other amino acids. Those other amino acids can influence the pKa, because whether or not it's going to give off the proton or not can be influenced by charges around it and whether it makes it more or less stable when it gives off the proton, right? So the point here, the important points, know what general acid-base catalysis are, and with respect to histidine, appreciate why it is that histidine would be in the active site of a number of enzymes. So what do these things look like? If we have something that is general acid catalyzed, then the velocity of the reaction is going to be high at lower pH, and then it's going to drop. All right? And let's say in the case for imidazole, okay, if it had a pKa around 6, then you'll see an inflection or a midpoint there that corresponds to the pKa of the buffer or of the ionizable group of a side chain that's important in the slow step of catalysis. This kind of a curve rising from low pH as it goes to high pH is reflective of general base catalysis. It tells you that in this case, it tells you that you have something at the slow step in the catalyst or in the enzyme that has to be in what form? The protonated form. This tells you you've got something in the slow step that needs to be unprotonated so that it can function as a general base during the slow step. All right, so what I just said is mostly true. It's mostly true that when you see what we're looking here, this is the pH rate profile. So here is something which functions only as a general acid catalyst during the slow step. During the whole process, it's going to function as a general acid at some point, general base at some point, but during the slow step, the rate determining step, it has to be in the protonated form, so it's going to work better at low pH, worse at high pH, and the opposite for something that's functioning as a general base. So here we have a slope down, slope up. So now let's say we do a pH rate profile for now an enzyme. So we're moving away from that simplistic chemical catalyst. What we will see is typically a bell curve. All right? So there are a few points here. The first is, let's say you had one entity that had to be charged or not. You wouldn't necessarily see this bell curve, but this bell curve tells you, right, is really you have one curve like this, which looks like a what? A general base curve, and you've got another one which is like a general acid curve, and they're being superimposed. Okay? So before I give you the specific, just think about this. Don't look at cysteine for right now, but let's just say you have two things in the slow step in the active site. One thing has to be positively charged, but then somewhere else in the active site you need something that has to be negatively charged. And they both function during the slow step, but this one during the slow step has to be positive, and this one during the slow step has to be negative. So if you did the reaction and it was at a very low pH, this guy would be positive. It's in the proper form to do what it's going to do, and if it was general acid-base catalysis, if it was positively charged, it would probably be functioning as a what? A general acid. This one over here, if it's negatively charged for that slow step, the implications are it has to function as a general base during the slow step. If the pH is very, very low, this guy, he's fine. ready to go, I'm willing to work. This one's already been protonated, and it's not negatively charged anymore, it is neutral. So low pH will be fine for one residue, but not for the other side chain. If you flip it and say we're now at high pH, this guy is happy. It's already in the dissociated form, so it says I can accept a proton during that slow step if you need me to, so I can function as a general base during the slow step. The other one, at high pH, already let go of its proton. So it, right, if it was like aspartic acid or whatever, it's negatively charged. Or if it was histidine, it's neutral. It can't do what it's going to do. So that should tell you that if you have two things that are contributing to the slow step, and they have to be in opposite ionization states, then at extreme pH, one way or the other is not going to work. You have to have a compromise, and that's why you have this. Right? Is that clear? All right, so having said all that, there are two other points to this, which is papain. It's a protease. First of all, when you look at these curves, you can see where there's the midpoint. So then you could project down and say, well, what do we know about these curves? We know that when you see a pH dependence like that, the midpoint of the curve is usually reflective of what? The pKa of the ionizing group. So you could look there and say, well, this is like 4.2 or something like that, so it kind of sounds like it might be a side chain corresponding to whatever amino acid. The problem with that rationale, and this really demonstrates it, is that the active site perturbs pKa's. So when we talk about pKa's, and we'll see other specific examples of it, you have to appreciate that there's a caveat to the pKa's. Sometimes, like when I'll give you on an exam, let's say a peptide, and where are the charges and so forth. Under those circumstances, you can assume that those side chain pKa's are what they are for the free amino acids, because you've got a short little peptide. It's not like you have this three-dimensional structure that are being brought together by hydrophobic effects, van der Waals, hydrogen bonds, salt bridges, so that things are in very close proximity, and then they can influence each other's ionization potentials. All right? But in this case, it turns out that the two residues, the two side chains that are involved in the slow catalytic step is a cysteine at position 25 and a histidine at 159. So the first point is, it turns out that cysteine, and this is an aside, really, when you look at that, it would give you the impression that you have something functioning as a what? A general base, right? But in fact, this ionizing group, then this cysteine, the self-hydryl, which has lost the proton, that can then do a direct attack. And we're going to see something similar to that with the serine proteases. But the point here is cysteine is now contributing, and it's undergoing ionization. And what is its normal pKa for cysteine? If you were at the exam, you could look on the table that I'm going to give you. It's around 8. Here, surprisingly, you say, I identified this cysteine as being important, but it's exhibiting a pKa in the environment of the active site of like 4.2, right? So if you think about it, cysteine normally would give off a proton. With a pKa of 8, does it normally do it very easily? It's a higher pKa, so normally it doesn't. If this inflection here in the curve is at 4.2, that says what? That the local environment is making that side chain easier or more difficult to release the proton. Easier. So something around that, positive charge, whatever, is helping that out. Histidine, we know, has a pKa of 6. So you always have to kind of wonder. It turns out here, this histidine 159 is actually exhibiting a pKa of around 8.2, which is making it a weaker acid, right? So, important points from this experiment. Number one is very classic that you see a pH optimum. And that pH optimum is reflecting all of the ionization states of things that are needed during the slow step, right? So if we simply say velocity is a reflection of what you're getting, but what you get is only as good as how you're going through the slowest step, that rate determining step. So in that rate determining step, there can be charges, there can be functional groups that exhibit acid-base behavior, and they have to be in the right ionization states. I gave you an example where there were two, but there could be more than two. And they could be in the enzyme, and importantly, they can also be in the substrate. So when you sort them all out, you're going to say a lot of these charges are in their right state for that slow step of catalysis at lower pH and not so much at higher pH and vice versa. So when you put them all together, you're always going to get a peak, right? And that peak is what? That's the pH at which you have the greatest number of molecules combined of both substrate and enzyme that have their ionizable groups in the right ionization state to carry out the slow step. All right? Is that clear? I'm not seeing as many nods as I normally do. All right. Okay, so let's look at chymotrypsin. This is just an introduction. Chymotrypsin is a protease. It cleaves the proton, the proteins at the peptide bond, which is the same as an amide bond, and not surprisingly, it will also hydrolyze esters. So we're going to look in more detail on Tuesday really what the active site looks like and appreciate how that active site facilitates the hydrolysis of the peptide bond and also how it confers specificity. When you have a protein, the backbone goes on. It's bland, monotonous, it's the same. What differs are the R groups. And so chymotrypsin will cut and hydrolyze the peptide bond, but it doesn't do it just anywhere. It prefers, okay, to cleave adjacent to these bulky hydrophobic side chains, and we'll see why that's the case. All right? It's the founding member of the serine protease family, and you'll see why there's an important serine in the active site and why there is a family. Okay, so as a lead-in to understanding the mechanism, just some initial observations that were done with chymotrypsin. So, as I said, chymotrypsin cleaves protein chains. It will also cleave and hydrolyze esters. So in this experiment, the workers took this ester, PNPA, which is here, and the product is PNP, and so they were able to look at the velocity, the rate of this hydrolysis reaction with chymotrypsin. So they're monitoring the amount of product. It was optically detected. It's not that important. It's just you're looking at the rate of appearance of your product as a function of time. So when they do this experiment, different concentrations of enzyme, so forth, what they would see is that initially there's a burst. So early on in time, you see a burst here, right? There's a steep rise in the amount of product, and then it would level off and stay at a constant rate, but a reduced rate. And so this basically was referred to as a burst phase, where you're getting a burst of product coming out, and then after that, the velocity is changing and you're going through a steady state phase. When they do the experiment at different enzyme concentrations, they would find that the size of this burst, right, in other words, how high up that goes, it was always equal to how much enzyme they put in. So if they put in more enzyme, you would still see the same burst like this, but it would just go higher before it plateaued. The rate of the steady state was proportional to the enzyme concentration. So if this was at one enzyme concentration and then another was done at a higher enzyme concentration, this would go up and then it would plateau, but that plateau rate would have a slightly different slope, okay? So how do you explain those results? They came up with a model for covalent catalysis, and we will see that there is, during the catalytic mechanism for chymotrypsin, there is a covalent bond that's formed between the enzyme chymotrypsin and the substrate. So when the enzyme locks on to its substrate, PNPA here, what happens is as soon as it hits it, right, you get acylation, which is adding the acyl group of the PNPA here, adding that to the enzyme. So here we have an acyl enzyme intermediate, right? This acyl group hooked up covalently to the enzyme, but what is the product? The product is this. So during that very first step, which is very fast, immediately you're spitting out product. What do we know about catalysts? What do we know about enzymes? It has to go back to its initial state. So at this point, you now have to get deacylation here and have that removed from the enzyme, and that is the slow step. Bless you. So kinetically, when they looked at the shape of these curves gave rise to a model, and then we'll see how it is mechanistically that it is in fact occurring, that the enzyme chymotrypsin, these serine proteases, their mechanism involves a covalent bond where the product is formed relatively early, and that is a fast step, and then later to turn it over, it has to be hydrolyzed off, okay? We'll talk a lot more about that on Tuesday. All right, exam issues. Okay, so first, it is Monday morning. Get here on time. Unfortunately, there's a class here before. So we're going to have to deal with that, and we're going to have to deal with the class coming in after. What I will try to do with assistance is get the exams to you as quickly as we can and give you as much time as we can. So if everybody's here on time, and I can, do whatever with the faculty member before, maybe we can try to get in a little bit early. But you want to get here, be ready on time. Number 2, you do not need a calculator. Okay? Not going to have you number crunching. What else? Enough to fill your time. All multiple choice. Now, in terms of the questions, I'll tell you ahead of time. Sometimes the questions are which of these statements is true or which is untrue. All right? Because you had mentioned something about exams potentially being tricky. No, but you have to read the question carefully, and then what you should do is on your exam sheet, just basically say, is this a true statement, is this a true statement, or whatever. Do that, and then go back to the question and see, am I asking you for which statement is true or which one is incorrect? Okay? Just go back and do that. What else? A handful of you have emailed me for some additional discussion, office hour type discussion. Those that have emailed me, I will email back just to confirm if you're not here. I have to teach another class this afternoon, but I'm willing to be in my office from 11 to 1. All right? So if anybody has questions that they want answered on not a grand stage or a recitation, come to my office. You should know where it is, and hopefully not everybody's going to show up and have lines down the hall, okay? How many people would potentially be interested? All right, well, I'll be there anyway, all right? Okay, last point. I want you guys to read this, and it's applicable to Monday, but probably just, if not more, applicable to life. In the past, when I've taught this, I've had students after the exam say, you know, I just don't know what happened. I knew this stuff. I knew this stuff, and I don't know why that didn't translate to my grade. And it, in my opinion, is exactly this. When you sit down, you have to be able to get control of your mind as best you can and say, what's done is done. I know what I know. I don't know what I don't know. And focus on the questions and just think about the science. Just think about the questions. For each question, try to remember the lecture notes. Try to remember how we talked about it. If you sit there and you think, I'm taking an exam and I have to do well, right? That just doesn't work. But it's not just an exam, it's everything in life, right? If you're shooting free throws in the backyard, no problem. 2 seconds left in the game, you see 2 rims. Right? You can't walk around thinking your boyfriend or your girlfriend is going to go off somewhere and worry so much that you don't enjoy your life or your relationship, whatever. Main point is you have to learn to relax. You have to learn to just focus on what's in front of you. And hopefully you guys will do that, all right? Any questions? Say what? You can practice Monday morning if you. All right. Well, I'll tell you what. If I check UB Learns tomorrow, I'll see if I can get more questions loaded up, which will be extra questions for exam 1. And if you have more specific questions you want to address, like I said, between 11 and 1 today, I'll be there. Just make sure you're here on time on Monday.
I have a really quick question. Let's say if you ask like a question on the exam, say what order of the reaction is this, and you're talking about the